Hey guys, in this video we're looking at a whole bunch of different ways to solve systems of linear equations. If you're in Math 98, this is just section 3.1. If you're in Math 94, this will be sections 3.1, 3.2, and 3.3, I believe. So the deal with this is we have three different methods for solving and we have three possible outcomes. And so for our first method of solving, it's going to be graphing. And I'll use graphing to kind of show the three outcomes that can happen, and then we'll apply those to the next two methods. So graphing is probably the crappiest version of solving a system of linear equations we got. I'm going to take this one right here. I'll do a little XY table. And it's in standard form, so I'm going to use my intercepts. That makes it easy. When x is 0, y is 3. When y is 0, x is 3. And then I'll do the same thing over here. XY. So for this one, when x is 0, negative y is 1. So if I move that over, it'll be y equals negative 1. When y is 0, then the x is 1. And so what I'm going to do is I'm going to graph these two lines. So x is 0, y is negative 1. And when x is 1, y is 0. And I'll graph this one. So it's on the 3's. So it'll look like that. And then our solution is the point right here that satisfies both equations. It's where they intersect. And so this point is the only point that satisfies both of these lines. So it's the solution to the system of equations, because we're asking, is there anything that would make both of these true? So then just reading it off the graph, that's going to be x is 2 and y is 1. So you can see if I put them in, 2 plus 1 is 3, 2 minus 1 is 1. So that's our one solution. So one solution is kind of the normal thing that happens, and then these next two are kind of the oddball things that can happen. So for number 2, these ones are in slope-intercept form, so I will just use the slope and the intercept to graph them. So for this first equation, it starts at 3 and has a slope of negative 2. And then just kind of keeps doing that to infinity. And then the second equation starts at negative 1, but it also has a slope of negative 2. And if you remember when we did parallel lines, the slopes for those, they were the same. So that's what we're going to get here, is parallel lines. And since parallel lines never meet, that's kind of the definition of parallel lines, that's why this would be a no solution. So it's possible to have two equations and just have them parallel, so they'll never have a point in common. And then the third outcome that can happen is infinite solutions. So if I take this one up here in standard form, I'll make a table for that. If x is 0, y is going to be 2. And if y is 0, x is going to be negative 4. So graphing that, x is 0, y is 2. And then when x is negative 4, y is 0. So that would look kind of like this. And then if I go to graph the second one, so that one starts on 2 also. So that could be our solution, except then we go and we look at the slope, then it goes over 2 and up 1, over 2 and up 1. So you can see those are really the exact same line, just sort of written in different forms. So if I like multiplied through by 2 and brought the x over, then I'd have that equation. So what that means is it's infinite solutions, because these two equations are actually identical. Sometimes they're called identities also. So every point on this line is a solution to the equation. So for this, we would just say infinite. To elimination method, which would be the next section in 9.4 if you're trying to follow along with the book. I prefer these all kind of as one. It's just three methods of the same thing, so I prefer to show them all together. Elimination method is going to kind of be the workhorse. The graphing is not a great method of solving. There's all kinds of things that can go wrong. If you don't draw a straight line, it's hard to read the answer. Easier on the computer, but harder on paper. If the point intersects at something crazy, like 2/7, you're not going to be able to read that from a graph. And so that's why elimination method, this is really kind of the the one that we use a bunch, and it generalizes to higher order equations, we'll see later. Or not higher order, but more variables. So the idea of this in elimination is also sometimes called the addition method, and it's because we're going to eliminate one of these two variables by adding the two equations. And so for this, what we want to do is we want to get the same coefficient, but we want to have opposite signs. And so there's a few different ways there's actually lots of ways I can do that. But we're just sort of looking at what we have. I could do, if I did a -4 here, I would get a +4, -4, and that's what we're shooting for, is to get same thing, opposite signs when we add, they cancel. Or I could do a -2 across here and get a +14, -14. I'm going to go with that one just because I try to go with the smaller number whenever possible, so I keep smaller numbers. And this thing I'm doing here, where I'm putting parentheses around the whole thing, is actually bad notation. I should do this. It gets really messy, so I tend to just do that, but that's the proper notation that I probably won't use, but that's what I should do. So multiplying this 2 through, I'm going to get 2x and then plus 14y equals -28. I'll just rewrite this one right below it. And then this is going to go -2x, those cancel, that equals 0. And then I'll divide over that -2. I can kind of see what it's going to do already. So then x is 0. So what that does is it gives me the x coordinate of where those two lines would be intercepting. And then what I can do is I can just, once I know x, I can toss it back into one of these original equations. I'll just arbitrarily pick the first one because it has little smaller numbers. So that'd be 0 minus 7y equals 14. And then you can see I can solve that for y. So the 0's not doing much, so we'll just say 7y equals 14. And then divide this, and get y equals -2. So when you put these in the computer, make sure you put them as an ordered pair, not 0, 2, but 0, -2, but you need the parentheses to make it an ordered pair. So next example, also using elimination method. So I'm looking to get either positive, like a -6, +6, or -2, -4, +4. And if you look at this one, you kind of see what it's about to do. If I multiply this whole thing by 2, like if I was aiming for the 4s, you can kind of see I'm going to get this thing but backwards. So this would be -4y, and this will be a -10. And then if I just copy this one down, and then gone, 0, and then gone equals 0. So this is what the infinite solution kind looks like. So the one back here where they're actually the same line. When you solve them algebraically, if you get like all the variables drop out and you're left with a true statement, that means it's going to be infinite solutions. And we'll see a little bit later, if we get like 0 equals 7 or something, we get a false statement there. That's the one that's going to be no solution. So that's sort of how we can tell those two things apart. For number 6, we actually have to do a little bit more work. I got 3s and 5s, and I got 2s and 5s. So I would probably go with the 2s and 5s just because they're a little bit smaller number. And I need to make these be the same thing. Again, opposite signs, that's always the goal. So when we add, they cancel. So the smallest thing I could do there would be a 10. And so I think I'll do the top equation by -5, because that's going to get that sign reversed. And I'll do the bottom equation by +2. And then that'll give us a -15x, a +10y, and a -10 there. And then doing this one by 2 gets me 10x minus 10y equals 20. And now that I have these set up, I can cancel those out. This will be -5x equals 10, and then dividing over, I get x equals -2. And then once I have this, I just come back up and I back solve. So that would be 3 times -2 minus 2y equals 2. So -6 minus 2y equals 2. I can bring that 6 over. So Now I'm just trying to isolate y. That gets me 8, and then I'll divide the negative 2 on both sides, and y equals negative 4. So a solution set would be negative 2, negative 4. The next, I think 4 examples, yep, looks like 4 examples coming up are all the ones I would have you try in class. So looking at this first one, it looks like if I did a negative 2 across here, that would knock out that would make this a positive 4, negative 4. Actually, let's just do a negative 1. That'd be even easier. I guess in the notes I did a 2, but that's okay. I'll do the 2. Nah, I want to do the 1. Forget it. 1's easier. Being indecisive, sorry. Okay, I'm back. So negative 1 times negative 2 is going to be a 2x, and then that's going to be a plus 9y, and then that's going to be a 25. And then copying this one down equals negative 23. And then this is going to go negative 2x, that canceled, and that equals a positive 2. And then I can divide by the negative 2, and x equals negative 1. So once I have that, I can come back to the originals. I'll just grab the first one arbitrarily. So this will go 2 minus 9y equals negative 25. And then I can bring the 2 over. And then that cancels. I'm left with negative 9y equals negative 27, or y equals 3. So solution would go negative 1 and 3. Okay, for number 8, let's see. I could either do a negative 5 and get rid of this, or I could do a negative 3 and get rid of that one. I think I will go with the smaller number. So this is going to give me a negative 3x, a negative 6x, a negative 3y, and a negative 60 right there. And we'll just copy down this one, 6x minus 5y equals 12. And then x's drop out. Negative 8y equals negative 48. And then divide over the negative 8. And y equals 6. Again, just plug it back in. First equation looks easier, so I'm going to do that one. And I can scoot the 6 over. And 2x equals 14 divided out, and x equals 7. So our solution set's going to be 7, 6. Number 9, let's see. How about we do, what did I do in the notes? Yeah, so this has kind of 2's and 3's and 4's and 6's. So this I'd have to bring up to 12. This I only have to bring up to 6. So it makes me want to do a negative 3 right there. And a 2 right here. So if I do that out, I'm going to go negative 3 times 2 for negative 6. It's going to give me, oops, with an x. And then negative 12y equals negative 24. Do the same thing here, run the 2 through and get 6x plus 12y equals 20. So then you can kind of see what happens over here is all that drops out and I'm left with nothing. Over here, negative 24 plus 20 is going to be negative 4. And so this is what it would look like if it's a no solution, as you get that false statement. And then number 10, let's see, I could either make the 3 and the 5 into 15s, or I could just do this one by 8. So I think that's less work, so I'm going to go with that option. And so let's see, that's going to go negative 40x plus 8y equals negative 24. And then I'll just add this one to it. So then this side comes up negative 37x, that drops out, but then this side's nice because I get a 0. So then I can divide over that negative 37. Not x, and x equals 0. So once I got that, plug that back in. First equation looks pretty easy. So I'd have negative 5 times 0, so that's nothing, plus y equals negative 3. So y equals negative 3. Solution set 0, negative 3. Okay, then we got last method of solving is substitution method. And graphing we don't use a ton. Elimination method we use lots and lots and lots. And this one's kind of the in-between one. There's places where it's nice, but it's not as useful as, say, elimination method for solving systems, at least. So the idea with this is that we're going to kind of combine, we're going to substitute the two equations so that we eliminate a variable and get it down to a one variable equation. So this one is set up y equals 5x minus 7. So I'm going to take this 5x minus 7 and put it right there for that y. And that's the substitution. And so you'll see once I do that, so I'm bringing down this negative 7x, and then that minus 2, and then all this stuff goes in for that y. But once I do the substitution, you see I'm all in terms of x, and now it's something I can solve. So I'm taking my two equations and rewriting them as one equation and one variable. So that's kind of goal substitution. So I'll do a little distribute there and get negative 7x minus 10x. That'll be a plus 14 equals negative 3. I can combine those two and get negative 17x. I should be good and show my steps. Here we go. And then that plus 14x, I'm going to scoot over and go minus 14 on both sides. So that all drops out, and I got negative 7x equals negative 17. And then we divide it. And we got x equals 1. And then once I have that, you're going to have one equation that's already set up to substitute for the y. So just go back to that one. And then you got y equals negative 2. So 1, negative 2. For number 12, this one is set up more like the elimination ones were, but I just wanted to do one to show it's not a big deal to rearrange it often. So in this case, and probably if I ran into this without the directions, use substitution, I would probably just do elimination, but I could add this x over pretty easily and isolate that y and get x plus 3, so I'm going plus x. And then that allows me now to take this piece and tossed in for that y. If the x had been easier to solve for, I would have solved for that one. I'm just kind of going for whichever variable is kind of the path of least resistance. So I'll go ahead and take this and toss it right there. So negative 3x plus 3, and then our x plus 3 goes in for the y, and that equals 4. And I can distribute negative 3x and then plus 3x. That'll be a plus 9 equals 4. And then you can check out, so those drop out, and I'm left with 9 equals 4. So there's an example of kind of what a no solution would look like via substitution method. And if it was infinite solutions, I would have got something like 4 equals 4. I would have gotten a true statement instead of the false one. So that's a no solution. Okay, and these last three are the ones that have you try in class. So take this, solve for x already, and just toss it right there for that x. So that's going to look like negative 2 and then times 2y minus 2, and then the plus 4y equals 4. And we'll just kind of distribute and go where it goes. So negative 4y minus and minus will make a plus 4. Plus 4y equals 4. And you kind of see right there, negative 4y plus 4y. So this is what I was just talking about. So that's going to be infinite solutions because it came up true rather than false. This one, we're just going to take this, and that's going to go in for that y. So that's going to be like negative 3x plus 6, and then 5x minus 2 right there equals negative 12. And then same old distribute and solve that we've been seeing. So negative 3x plus, that'd be 30. And 6 times negative 2 for negative 12 equals negative 12. And then this one, we can go negative 3 plus 30, and that's going to be 27x minus 12 equals minus 12. So then when I bring the 12 over, I get a 0. So then that's going to be 27x equals 0. So notice it's not 27 equals 0. That would be a no solution. This is 27x equals 0. And so it means I still have a path to solve it. It's not a false statement. We get x equals 0. And then tossing that back up here, 5 times 0 minus 2. And so our y is negative 2. So 0 and negative 2. And then this last one, it's not set up for substitution, but I'll show you how you could. So if we had to substitute on this, I'd probably get that x by itself just because it's the simplest. So I'm going to subtract the 3y over, and I get x equals negative 3y plus 12. And then that gives me my expression that I can substitute. So I'll take this and drop it right there for that x. So negative 3 and then negative 3y plus 12, and then minus 9y equals 7. And then again, just kind of follow the math. So 9y, 36 negative minus 9y equals 7. You can see the variables are dropping out. I'm left with this very false statement, so that is a no solution. Okay, so that wraps up two variable systems of linear equations.